I just have to got it. Okay. Hello, good morning, good evening, everybody, wherever it might be. It is my great pleasure to welcome Magnus LANDSTAD all the way from Trondheim to Warsaw. We're also very happy for a change finally to have on-site speakers, not just online. And the room is actually quite full. So you can see us on the camera. We're also very delighted about it. He will tell us about his joint work with Steve Kaliszewski and John Quigg. And it is exotic group algebras, cross products, and coactions. The floor is yours. The Zoom is yours. Take it away.
Thank you very much, Piotr. And thank you for the invitation coming here. It's always been a pleasure to visit Warsaw. And also really even more pleasant to be part of a live seminar with real people. So, as Piotr said, this is talking about joint work with Steve Kaliszewski and John Quigg from Arizona State. And this will not really be a quantum group talk because I'll be talking about groups all the time. But as I promised, it will be more questions than answers in this talk. And of course, all the questions can also be phrased for quantum groups. And of course, there, well, maybe it's easier when you're in groups, I don't know, but I guess it could be more problems if you try to answer the same questions for quantum groups. Okay, so I start with that didn't work. Content, right? First I talk about what's called exotic group algebras. And in connection with that, I will sort of do, well, go down maybe a blind alley. I call these are groups, because I think they don't exist. And after that, I would suggest we have a small break. But before I go on to sort of do the same thing for cross products and finish with some open, well, more open questions. So, given a locally compact group, we sort of know two C-star algebras which we are used to work with. It's the regular group C-star algebra, defined by the regular representation, and sort of the full group algebra, which are given by the sort of universal representation. But already in 1964, Aymar noted that there are, in fact, lots of algebras in between. So I took it out for. So if you see this down here, no.
You have to click on this number 3. Yeah. Yes. So yeah, exactly. Oops, no, not somehow. Maybe stronger. No. Okay. We'll put your finger on this number 3 and keep it for a second.
I see.
Yes. Now it's good. Okay. No, what's wrong?
Well, anyway, it's on the bottom. It's I don't expect to read it, but at least what you see is that
I don't know why.
It shows that one can, in fact, define other more group algebras by simply taking representation in between the regular representation and the universal one. 12. So, that was clear, I think. And
so these other versions depend on the choice of a norm.
Yeah.
Mm-hmm.
Yeah.
So, different norms.
So until recently, there has not been so much interest in studying these algebras. It's not quite true. I'll get back to that later. But it's a paper of Nathan Brown and Gittler from quote our interest. But these algebras in between are interesting. And also other work has been done by Beatrice and Tuset and also Kayak Sultan. I've studied similar question for. Okay, so what shall we do? Well, we are looking for algebras between the regular one and the full one. So we always know that we have a map from the universal one down to the regular one. And we want to look at things in between. So that means that we have here's the regular representation. We have some other representation of the C-star algebra of G, which is then, of course, a portion by some ideal. So this ideal is the kernel is an ideal in C-star. And we call this algebra exotic if neither of these are isomorphisms. And we shall also need the dual spaces. So for the Fourier steepness algebra, we call B of G, and also the dual of the regular C-star algebra, we call B of G. And if you have something exotic, we look at the corresponding dual space. So, yeah, that will be sort of the annihilator of the ideal. And so these will be G invariant subspaces of B of G with certainly this containment. And well, it looks sort of hopeless to look at all these possible spaces. So we are going to restrict it a little. So looking at this diagram here, which here G is discrete just to make it a little simpler. So this here, yeah, that's the same as we started with. And you see the left part here is the same, right?
Yes.
And sort of this map is simply a lambda tensor identity going down there. And this Q goes Q tensor identity here, etc. So what we are looking for is there a map going directly in here that we what we later call coaction. Map from this algebra into the algebra tensor C-star of G. So and the map between C-star G and this tensor product is simply the one which sends group element G to G tensor G. So that's sort of a well-known map. And sort of the first theorem is that this map exists if and only if this annihilator in the first steepness algebra is a G invariant ideal. So that, of course, that restricts.
I have a question.
Yeah.
Is it automatic that this ideal I is invariant with respect to this correction of this universal C-star of G?
Well, it's invariant under translation of G. So as a subspace of B of G, so the translate by a group element is that's the part of
but invariance is about the action of G. But this is invariance with respect to the correction of C-star of G.
No, not yet.
Not yet.
No.
Okay, okay. So something is happening here. Okay, not sure.
So, okay. So, sort of this, so we call such a quotient large if it's sort of between the regular and the full C-star of G. So I classify by large ideals of B of G. So that means G invariant weak star close non-zero ideals. And in fact, then it's automatic that it contains the Fourier steepness algebra.
So just a stupid question. What do you mean by E perp with this perp on the left-hand side?
Yeah, so that, yeah, so there is a duality between the space B of G and C star of G.
Okay.
And this pre-term is simply the functionals which kills the
Okay.
idea.
Okay,
Yeah.
okay, I've got it.
Annihilate.
Gotcha. Yes.
I think I got that wrong. That's the element of G, C star of G, which are killed by E.
Mhm.
Yeah.
Okay,
So usually we would have it on the other side, but
yeah.
when you go to the double reverse.
Mhm.
So it appears that there should be a lot of these ideas. And okay, so the first examples what we found in Brown and Gintner, that sort of you take functions in B of G, which are also in LP. And well, that may not be weak star closed, so take the closure. And for some curious reason, it turns out we can't just take B of G intersected with LP of G. That creates some problems. So we need to this subspace, which might be smaller. We don't quite know that, but at least that's what they proved. That this is a large ideal in B of G.
What is meant by a large ideal?
That's I said here.
Okay.
It's an ideal in B of G.
I was thinking about that.
Yeah. So, okay. But basically, it's an ideal between BR of G and B of G. And well, as I said, this has been studied before. For instance, Godemang proved, that's a long time ago, that for unimodular groups, the functions in B of G, which are in LP or P between 1 and 2, they are all equal to PR of G. And later, Alan Carey proved this also for non-unimodular groups. And sort of more recent result by well, Dixon, Uzawa, and also partly independent by Brown and Gintner. They showed that for a free group and T larger than 2, we sort of get a continuum of ideals. And
sorry, are there some containments between these ideas?
yeah, so since the functions are bounded, EP will be containing EQ in this case.
Not different.
So it will be sort of increasing. And also for a connected group, there's a proof for SL2R, sort of the same thing, but there is a continuum. And I think, in fact, he also proved that these are all large ideals in this case. But the strange thing is, if you go to SLNR for n larger than 2, it turns out that for after n, they're again all the same. So they are different between 2 and n, and then they become the same, and then they are the same for p less than 2. So,
but below 2, still they are equal.
yeah, so that was, this is unfair. That is for all groups.
So in this Godemang-Carey, G is not necessarily discrete.
No, so that's for a general locally compact.
General, locally compact.
So, and so on the note here that, I mean, for semi-simple E group, the study of square integrable or square integrable representation is a long study for a long time ago. I mean, in Dick Smear's book, there's one chapter about about this, and of course this is part of the big theory about Algebra stuff about Lie groups in the 60s and 70s. So it's not quite true that these algebras or these ideas in between has been ignored, but at least we put them back to life.
Sorry, in this Scaramucci theorem, it is not known what is happening between 2 and n, or?
I think it's known that they are different, just like
Still there are.
like here. Yeah.
Yeah.
There are also some other results that I mean, they are contained in each other, but I think also they still are isomorphic. So it's,
And in this theorem by Hickson and others, nothing is known about free groups on more than 2 generators, just F2. Or are there any results for Fn, F3?
Expect the same thing to be true, but it's the F2
So one could expect something similar to Scaramucci, but instead of the rank of the group, the number of free generators could create some island of inequalities between 2 and something.
I'm not sure.
Did you have in mind this?
I think so that's I need to write something here, and then I to share.
We should press yes, 0.5, yes.
So
No, it didn't work.
it work?
No,
Very happy to answer.
Sorry, there is a comment on the chat.
yeah, go ahead.
Yes, the comment is that it is the same for all Fn, including F infinity. So
You just checked it, or
my
you just
comment.
proved it. You just proved it.
He proved it by reading it from the chat.
So who is
Yeah, sorry.
who's chat?
No, I'm pointing to the comment, but this is not my comment.
Okay, so it's Adam, thank you so much.
Uh,
Yes, great,
The
okay.
comment is also by Adam, so.
Yeah. I thought that you just proved it, okay.
Because the example by Uffe Haager is to take the length function on F2. And A is just any number. Then this is a positive definite function. That's represented by Uffe Haager. Well, it's easy to compute the LP norm for this function because it's an exercise, really an easy exercise to find out how many group elements have the same length. And then you try to compute, for instance, L1 is just computing the policy. Yeah. So then it's easy to see for A is your LP or not. So this, and I guess like this, something similar to for anything. Okay, so. Okay, so how do you get? Yeah, so that's one example, or a series of examples of getting large ideas. And so for the construction Brown and Ginter, it was to start with an in this discrete case, so it was an infinity of G. Just take an idea in continuous bounded function, and then we simply take the positive definite function in this class, and then generate a large idea. So, a question: do all ideals arise in this way? Maybe not. And as we saw, it certainly will not be a one-to-one correspondence. And so another example is by Hogger, which we call the Reichmann algebra. So we take B of G intersected with C naught of G. That is not closed invariant ideal in B of G. And we take the B closure because I guess it's not necessarily closed. And then sort of he has the Hogger property if and only this is the of B of G. And well, and that sort of the easy part of that proof is clearly this function here is the C naught function. Because A is less than 1, so that makes it 0. And sort of yeah, but maybe before I do this, I give you another example which I forgot to put on the slide, which because we have B of G can always be written as a sum of the almost periodic function and plus something else which well, I guess it doesn't really have a name, but I call it IP of G. So, of course, a P of G, that's generated by a finite dimensional representation or coefficients of finite dimensional representation. And the rest is that what we take representation with no finite dimensional sub-representation. So this is clearly, that's a subalgebra. And this turned out to be an ideal. Well, that was the basic, that's the results which I learned from Martin Walter, one of his papers. And that result, not so very difficult, it depends on, you take tensor product of two unitary representation of a group. That can only have a finite dimensional sub-representation if both representations are started with an as-is property. So you can't take sort of infinite representation. The tensor product will contain no finite dimensional sub-representation. So that's another example, which we haven't, I guess, yeah, I sort of forgot about it, but it occurred to me last night. Okay, so the Brown and Gintner, they have sort of a different approach than we have. It looks very similar. Simply start with an invariant subspace of D of G. So, and then you can consider E representation. That means the representation for which a dense set of vectors, the coefficients are in this subspace. So that's typically one does for square integrated representation, etc. So then you can form a quotient, which we call C star D from there. But taking the intersection of all the kernels. And yeah, there's some fine print here. If you want BRG to be contained, that may not be automatic. Okay. So, well, simple case, if you take all representation, of course, we get C star value. And if you sort of did what we take, I guess we call it EP of G earlier. So P in 1 and 2, you simply get a regular representation. And yeah, I guess this is what we talked about earlier for n equal 2. So I guess
Yeah.
I forgot that term later. So then you get a continuum of yeah, also for Fn. So there are a lot of. So what we did here, we already, there's one way of taking the kernel, and we are doing something slightly different. And one would think this two construction should be the same. In fact, in an earlier version of this paper, we thought that too.
Sorry, if I might, what is the difference between annihilator and pre-annihilator?
Well, sort of D here is a part of B of G. So that's the dual of C star of G.
It's like dual and pre-dual.
Yeah,
This.
yeah. So this is
Okay.
a step down.
Sorry.
In the double dual. Yeah, well, it turned out that we were wrong, and they corrected us. One issue of an but you need something like this. But E expand by its positive definite function. Then the two construction lines. And well, for purposes is enough to be but is this true or not? In general, we don't really know. Even for well, there's a positive answer if this algebra, if D is not closed. So in particular for this Reichmann algebra. But for LP, we don't really know.
PG is positive multipliers.
What?
P of G.
P of G is again the dual of C star of G, so it's the Fourier stiffness algebra. The B of G itself is spanned by the positive, its positive definite function. But if you take B of G intersected with alpha, you don't know the person hoping maybe someone you could answer it. Okay. Now I come to something which well,
Okay.
this will be I mean, in general, there seem to be many large ideas. I mean, series of LP, etc. And that sort of give the opposite is true. There is accept the have a non-amendable group, so at least we have BG and BR of G, but nothing in between. And that was the question asked by Tim Delat 3 years ago. And I mean, should one have a BRG? It should be the regular part, and then just the constant thing. And well, that would be rather bizarre. So if you go, that's such a group bizarre, and the conjecture is that there are no bizarre groups. And so the next 10, 15 minutes, maybe a talk about the empty set. And well,
Sorry, so this conjecture contradicts the Gromov principle.
This is
Yeah.
exactly what I want to mention, that, yeah. So usually what happens is that there is, for such a general conjectures regarding groups, usually there is some exotic example.
yeah, so maybe I can stop here. But of course, at least my first reaction that was, of course not there, because I sort of believe in the 0-1 infinity principle. If you have a problem, either there's no solution, or exactly one solution, or infinitely many. But at least when you're teaching linear algebra, that's yes, but not. So, well, so we started thinking about it. So, what I want to do now is sort of give evidence that such groups do not exist. So, and okay, so some notation there which we still might need: regular representation and trivial representation. And then we can form the sum of these two. So, well, so it's not too difficult exercise, but G is non-amenable if and only this is surjective. And of course, when if this group is bizarre, then it will be an isolated group. So in particular, you will have C star of G as a direct sum of this idea. And then it's, well, this is probably a more general lemma. But if you have any representation, then this proves G naught will give you some vectors of the representation. That's nothing. So, and from this it follows that such a group will be a probability group. And the proof of that, you should look at book, excellent book by John Zala. And well, when the group also discrete, then it will be finitely generated. So that's also something we find there. And such a group can have not trivial finite dimensional representation. So, yeah, give you that sort of elementary proof of that. If you have a finite dimensional unitary representation, which is not a trivial one, so since then these coefficients have to be in the regular representation, right? And if you then form with the sum, you get one simply by, yeah. And well, this is an ideal. So then this is in BL of G. So then the whole left side is an ideal. It's in BL of G. And well, this is 1 and 1 is in BL of G, and then you get a contradiction. Like that you get. So in particular, well, the group has to be in the middle there. Otherwise, you get one-dimensional representation. And also you can, it will have no proper subgroups of finite index. Because in that case, this will be a finite dimensional space. Yeah. I guess I may already have done that. Assume that this group is discrete, but that's a little lemma you need in that case. And from this, you also can show that you have a design group discrete and the proper subgroup, then the subgroup is discrete. So it means that such a group, all proper subgroups are amenable, which of course also seems strange. And it cannot contain the free group. So, because the free group has many and from what so two set cannot be without group, and it can be part of the subgroup from that proposition we just said. So, okay, yeah, I guess that's not so important. The action is not what I call green leaf amenable. We have an invariant mean on the L infinity of G mod H, which I think that's a property which sort of been forgotten because it's not the same as amenable action as one does now. And well, you say something about conjugate classes, which yeah. So if you have an amenable subgroup, then everything is positive definite on the subgroup. It's also positive definite as a function on G. Go into detail of this. And turns out that you actually from the regular system into this quotient algebra subgroup. From what I show, it's probably true that you sort of have the proof that you have a normal subgroup. Most of it is done, but don't quite believe in the proof. So, but what you can always show that for bizarre is a unique maximal normal proper subgroup. So this has to be amenable. Of course, it's simple. So, well, at least if you believe the conjecture distance of some group implies a simple subgroup. Okay. So at this point, we have the conclusion that for a bizarre group has a property T and is finally generated. It has no non-trivial finite dimensional unitary representations. So that's a minimally almost periodic. So meaning AP of G is just the scaling. And all proper subgroups are amenable, and this quotient is integer. G cannot contain. And so, I mean, I was stating this hoping to reach a contradiction, but well, if I exist, there would be a non-amenable group not containing F2. And that's going to Grom's example. Well, so if anyone to think about something else, that's something to think about. All the non-existent with their own group background and so on, will give you some hints. So, group by the property. So now I suggest this Short break?
No, we don't break.
Well, I won't. Just,
So what we do is we wanted to stop the recording and
yeah, well,
we never have a break, so.
yeah, or doesn't matter, we have a discussion, at least I'm.
Yeah, we have a discussion. Yeah.
So maybe make a brief question. At the beginning, you talked about the coactions, the full group system around this intermediate one. So why coaction instead of just a co-product? From the coaction, you can construct a co-product because you.
Yeah, there it was the product, yes, for the group, so.
Yeah, but maybe co-product is more general.
Yeah, so I'm going to get into coaction the next part, so.
Are there non-amenable groups not containing F2, concrete examples?
Yes. Gromos examples. And
so, because I don't know anything about it. So,
no.
containing F2 is enough to prove that it's not amenable, or?
Yeah, so if it contains F2, it's not amenable. It was long conjecture that a non-amenable group had to go F2. That's not true.
So there are examples, but it's not like there is a classification that is non-amenable, then maybe it doesn't contain F2, but contains something else. No.
Yeah, I don't know. Something which contains a non-amenable group is itself non-amenable. So,
so the examples that one could check are, I guess, are really complicated. At least this case, right?
yeah, it's what's called the Thomson group, and some others. I've seen the definition, but I'm.
So maybe a non-discrete case is easier. Maybe there is something, for example, that that's because this is only the discrete case that you have all this problem.
Yeah, mostly, but I mean, you can formulate it also in Finnish case. Yes, that it's for continuous groups.
Groups won't satisfy Hagelhoff property. Will these groups satisfy Hagelhoff property? Hagelhoff property? Because they don't contain. I was thinking on the line that if it satisfies Hagelhoff property, does it contain F2? I mean, other than amenable case. So a non-amenable group satisfying Hagelhoff property, does it contain F2? Can you see that?
Well, F2 satisfies one.
Yeah.
Okay, well.
I think we are sufficiently broken.
Okay, let's continue. I sort of have tried to make a living of studying cross products and similar things. So, well, at least I've survived. Not getting rich, but at least so. For us, the natural step is going to consulting groups and see what we can do for the cross products. And then sort of we have the same situation. We have an action of a group on the C star, and you can form the full cross product and the reduced cross product. And from there should be a lot of things in between. And well, at least the definition, we stick to discrete groups because then it's easier to write things down. So when the full C star algebra, that's simply given by we take representation of the algebra and a unitary representation of G, satisfying this covariance property. And this sort of take a universal representation doing this. So in principle, we could take a large number of representations, not will take the sum, but it is a universal representation. And the regular cross product is sort of obtained in a similar way, just that we take a concrete representation of the algebra and of the group. And typically this, of course, is really the regular representation of M-line. And since this is a particular representation, there is an obvious map from the full C star algebra into the reduced one. And now you get sort of the first example of a coaction, even if I haven't defined what that is. Because see, we get a map from the full C star algebra into the full C star algebra tensor C star algebra, simply by mapping the B part.
Yes. Good. No, it didn't work. I don't know how to do it.
I have to take this.
Yeah.
This away.
Francesca, can you touch it? I don't know. Somehow.
It would look like a coffee machine.
Okay.
It's a universal. It's the first.
Sorry, the capacity of your skin, I don't understand it because each time I touch it, it works.
So the B part goes into the tensor identity, and the representation goes into GOG tensor G. So, and the maximum tensor product is worked out. Okay. So we do the same with the regular representation or regular cross product. But then we go into the minimal tensor product. So this is doing the maximum tensor product. Usually what we call it an R coaction, and this is sort of the regular coaction, which has been mostly studied.
And the slide, the tensor product was always the maximal one for delta and delta.
Earlier, I think didn't really tell you. And this part, my talk really should be dedicated to Ian Raven because
Since it was a special case of the course, kind of math, I guess.
yeah. So you may know Ian Raven recently passed away, so yeah. So answers of those technologies also looked at what then we call film. So now I define a general definition of a coaction. So an R coaction is simply an injection of any algebra into A tensor max C star G satisfying this property here. Where, I mean, so see, if you take delta tensor identity, that goes into A tensor C star G tensor C star G, and this one also goes into the same. So that's sort of the natural.
The coaction of C star of G, not of A. So you call it the coaction of A, but it's C star of G.
Yeah, so
on
C star
Yeah.
of C star.
on a sister algebra A.
Yeah, so sort of the group is sort of assumed. Yeah.
Yeah, definitely should be on, not off.
Yeah. And sort of the same, we simply do the same for the regular algebra. When instead of taking the main tensor. Okay, so now this point we sort of get to the Baum conjecture, and so very roughly stated that you have an action over local by C-star algebra. Then the K-theory of the regular, of the reduced cross product should be isomorphic to what's called topological K-theory. And I have no idea what this is.
RG.
So, in fact, if we are proving the bound constant, that is hoping that provide some tools. It will be useful. Know something about cross product.
But it's bound con with coefficients.
Yes.
Yeah, I think it's so. Yeah,
For G.
It's more complicated.
yeah. So,
Yes, Alan?
Sorry, shouldn't be there topological K-homology instead of topological K-theory?
Yeah, I mean,
yeah,
You mean this dual theory, yes?
yes.
Abstract elliptic operators, yes?
Yes, on the left-hand side, if a K-homology of a equivalent K-homology of the certain space.
Okay.
yeah. So this that shows that I really don't know what I'm talking about. But anyway, the problem is that this topological K-theory is an exact factor, but reduced cross product, taking reduced cross product is not an exact factor, and that's the result of the homology.
Yes.
So clearly, there's a problem here.
Yeah.
And yeah, so thus is the vulnerability in order sort of to solve this problem and studying cross-product factors. So that simply should be a factor from, if you have a C-star system, and that should give you a C-star algebra between the maximum or the, I said max instead of 2, I guess, and the reduced cross product, which are sort of, I mean, in both cases you have a dense algebra, that's taking sort of finite series of what we define. So it should be the same of this, but the norm is to.
Yes.
And such cross product factor is exact, sort of an obvious definition. Sort of an exact sequence of actions. So I is an ideal in A, B is A mobile. So it's that corresponding, there are maps between the cross product, and that should be exact.
So beta is induced by alpha, right, on B, because it's just.
Yeah, so Yeah, I is
Ideal.
is always the same here.
Yeah, so you restrict, but here you just induce.
So that will be sort of the quotient actually. And then the full cross product would be by Russell product. But the reduced cross product is not. As I just said, and in fact, that's the definition of the grouping. In fact, is that
Yes.
and then also other properties which are interesting. Also one study functors which are Morita compatible. It simply means that if you have two algebras with actions which are Morita equivalent in a nice way, the same should be true for the cross product.
But sorry, could you just quickly explain what does it mean to be Morita equivalent equivariantly? So, Morita equivalence is not the usual notion of morphism; it's just by module, yes. So.
Yeah, so it means that first that A and B has to be Morita equivalent. So we have a sort of a module, A acts on one side and B on the other side. And you have actions on A and B and also an action on the module. So which respect the actions of A and B.
So sorry, this equivalence by module should somehow be also carry also two actions of A and also of B, yes? And this should, I presume that this should be somehow compatible, yes?
Yeah.
Is it the action of G on this bimodule?
Yeah, so. But anyway, if
one could imagine that the condition should be something like this. Let's say alpha of A times the element of this bimodule is the same as beta of G acting. I don't know.
No.
I'm not quite sure. I'm not.
So this bimodule should have also two actions of G from the left and from the right.
Yeah, I think that's true. I need two actions.
Yes, exactly. That's what I meant.
Yeah. So at least there is a natural definition which I have written down. Okay, and it turns out that this seems like a property which often will be true. At least full and reduced cross product.
One action is enough, because if you have one action from left and one from the right, you form a joint action, which should still be an action. And then when you multiply by A, the right one doesn't play a role, and when you multiply by B, the left one doesn't play a role. So if you use only one,
Yeah, it could be. Yeah. I'm not quite sure we had to.
Otherwise, it would be pi equivariant.
Yeah, at least there is a natural definition of this, and well, simply you can take, if you have this module, you sort of take a cross product of this module will give you the Morita system. So when they show that this cross product factors, they're sort of ordered. I mean, one is larger than the other if you can map the cross product into the smaller one. So simply a question of morphism of C-star algebras. And they show that is a unique, minimal, exact, and Morita compatible cross-product factor. And the conjecture is then that this cross-product factor is the right one for the bound conjecture. Well, at least there are counterexamples to the sort of the first conjecture I stated, but they disappear from that.
Yeah.
But it's still not known if this is really solves the problem of the conjecture.
So Adam, you see that here Magnus wrote K homology because you have lower star applied to a space. So
Yeah,
Yeah. Yeah.
I stole this. Okay, so our program then is when you study cross product, you should also do that by using coactions. So our program is so-called their program is so-called have an action, you construct a full cross product, and then we use a coaction factor to get this exotic cross product. So,
sorry, I have a question. So you are changing the philosophy. Because instead of Morita compatibility, you have this dual coaction.
Yeah, so yeah.
But there is some principle in some cases that dual coaction cancels Morita. Yeah.
Morita is coming back.
What's the situation now? So in the sense, the philosophical approaches are similar.
Well, what we are doing, we are sort of replacing action by coactions and trying to do the same thing as I do for actions on coactions.
Yes, so I'm trying to imagine what's the relation with this Morita compatibility then. It is in the style that dual coaction cancels the action up to Morita. Is this analogy between these two approaches? Philosophically, at least.
This is a conjecture that you always have delta sigma, or
yeah. So that's a conjecture really. That for every cross product factor, you can find a coaction factor such as this diagram commutes. So sort of our philosophy is that every cross product factor, then there is a coaction factor, which.
So, but the conjecture is that the tau exists, but the delta sigma we know that exists is.
Yeah, so that's part of the construction that for a coaction that we also have a certain coaction there. So the coaction factor then simply is a factor between coactions. So start with the coaction, and this factor maps A into a smaller algebra, presumably, and a coaction on that algebra. And together with natural transformation, and which should satisfy some axioms which you don't want to see. And then, in fact, we can prove the same thing as they did. It is a unique, minimal, exact, and Morita compatible coaction factor.
Yeah, I understand.
So, and of course, I haven't said what the Morita compatibility is. But, so that's okay. And well, okay, now we want to see are sort of interesting things in between the full and reduced cross product, and similarly for coaction. So we get back to this large idea see that will give us coaction function. Simply because, let's see, we have, this is the coaction, goes from A into C star of G, and then we map C star of G into this quotient algebra given by this large idea. So the C star of G is a quotient from C star of G, so therefore we get a map. And yeah, so yeah, we get similar maps here on A.
Is the use of this character E for this large ideal
That's a very bad,
premeditated
no,
to say that it's an exotization?
no, the notation is very bad. I mean, we call well, we use the E for ideals, E, F, etc. And so for a given E, it's define realization. We didn't come up with anything better, but I agree, it's not a good way. So, well, E sort of exotic in the background, but
You know, it might be irrelevant, but it very much reminds me of what we were doing with Sergei Neshveyev and Ludwig Dombrowski when we wanted to injectify non-injective coactions, because somehow we insisted that coactions should be injective. We assumed that coproducts are injective. This was our definition of a compact quantum group. And then, so it was in the compact setting, the quantum group setting, compact quantum group setting. And then we studied this functor, actually it's a functor of injectification. So if your coaction happens to refuse to be injective, you can force it to be injective exactly by such a construction as over here. And actually it has some nice properties. And I'm pretty sure that it's the same kind of quotient.
and sort of examples here are not very impressive because, well, if you take the ideal to be BR of G, you get what we call a normalization, and that simply means that we match things into the regular C star algebra. So we get sort of ordinary. So if you have sort of a back coaction, that maps you into regular coaction. And well, if you take B of G, of course you get nothing, because well, this will simply be the identity map. So, and for coaction, there's something called maximalization. It's at least it corresponds to when you have an action of a group on a C star algebra, you can take the maximum of the universal cross product. And that's similar. So, but so of course that means for any action we get sort of an exotic cross product with for this large idea. So we simply take we have an action first we form the full cross product, and then we use this function by the large idea. And at least that property is nice and Morita compatible.
And by compatible, we mean what? Invariant or? I'm
No,
not quite
again,
understanding.
The previous sense.
yeah, but if you have some surrounding graphs which are Morita on a Morita module or Morita equivalent,
When tau e gives
With
this.
coaction, and then also
Okay, so not invariant, okay, because Morita
in the sense that
it's equivalence on left-hand side and the right-hand side, and okay, and tau e maps things that are Morita equivalent on left. Morita.
Morita equivalence induces an equivariant Morita equivalence.
Okay, okay.
And it sort of has something I haven't talked about, the ideal property, that if you have an ideal, then that ideal is mapped, that map is injected. But it's not exact. Simply, well, because you know that for BR or G, that gets us the regular cross product, which is not exact. But of course, if it is exact, then composing with the full cross product, we get an exact cross product. So in that sense, okay. So then we can start looking at large ideals for which this factor is exact. And that turned out, well, could be an interesting property. And in fact, we show that if you have two large exact ideals, then the intersection is exact. And from that, it follows that the intersection will be the same as the products will be dense in the intersection. And in fact, I think that enough that model is exact, then that will be true. So that at least gives us examples of ideals which are not exact. For this ideals EP, so it comes from LP, then at least for a group like F2, if this was exact, this should be equal to EP, but that's not true. Okay. So another way of getting exact cross product is a construction of a bound Gintner Willett. What we do, well, you start with an let's see, you have two actions.
The title of your slide is kind of ambiguous because you can read it, how to get more exact cross product, or how to get more exact cross products.
All right.
Parentheses.
So if sort of you have two systems and you need a unit in one of them, C, because then you get a map from B into B tensor C. So that will be sort of equivariant with respect to action on B and sort of diagonal action on B tensor C. So that will also give you a map of cross products. And they define the C cross product as the image inside here. And that's my property. That turns out to be an exact thing. And I also get a minimal one. Getting this algebra be left uniformly continuous function. That's a abelian system algebra, so which I guess you're not so used to any longer. I took a general topology course many years ago. That was you learn that there's a difference between left uniformly continuous and right uniformly continuous, for instance. So sort of yes, I guess this might be the smallest exact cross product vector. But So we want to do something similar for coactions. And then there's sort of the same program. So, but here we really have problems if we use looking at discrete groups, things work out. So this, when I'm supposed to stop?
You still have 15 minutes.
Yeah, okay. I'll try to use less. Okay, so we start with the coaction, and we want to make a construction which also restricts to their situation if we have a cross product coaction. So now I guess we can, for a discrete group, it's sort of easy to say what a coaction is. Then it's simply sort of a Feldband structure.
Yes.
So we have a graded algebra. So the algebra has fibers over each group element, and in the property that multiply nicely, and take the adjoint, you maps into the image group element fiber over there. And then sort of we have two coactions. Then we can make a new Feldband by taking the tensor product of each fiber in the same. That's the problem. And then we take A and B are sort of inside some C-star algebra, so we can do these things. And yeah, well, I'm not going to go into that, but it turns out that we need D to be a cross product. Then things, so it's really given by an algebra C and a unitary representation. So then simply the grading, well, this will be grading of S will be the fiber over S here and sort of the DS. And we get the coaction simply by AS maps into AS into DS. The homomorphism. And well, so then we take the image, and it sort of turns out this works in this case. But sort of restricting to cross product, we get there cross product. This is an exact coaction factor, and the smallest one is for, since we are discrete, this will be L cross product of L infinity by G. So that means that for every such coaction, there is a map into this one. So it's a bigger, it's the smallest among the volumes are constructed this way by taking tensor product. It's not the smallest of all coactions. Okay. So that's really more or less what I want to talk about. But so there are some questions. Is this a minimum exact coaction function, which we know? You know there exists one, but we can't really say what it is.
So you want this analog of this theorem, which was proven not by Baum and others, but by some other triple. Right? Because can you go back in your slides?
Yeah, let's see. So
back. Yeah, still back. Yeah. So you mean like this Bus Echterhoff Willett?
Yeah.
That's so. There are questions about an analog of this theorem, right? Okay.
Yeah. So we have the analog of this theorem, but the problem is, as I guess I stated that it seems this may not be the smallest exact cross product factor.
Mhm.
It's the smallest of that kind. So let's see. And for locally compact groups, we start.
Wait, so what was your standing assumption on G so far?
Well,
Discreteness?
no,
Discreteness.
discrete. Because then we could use fiber buttons,
Yeah, this grading stuff. Okay.
And that doesn't work for the general case because coactions are not in general given by fiber buttons.
Right.
And well, then you have to modify the sort of the definition of what the coaction is. When you sort of just map into A tends to C stability, but you sort of sub-algebra of the multiplier. And also, you probably need to replace the regular tensor product by the maximum tensor product. Sort of following the engravers. So, okay, we want to sort of have the same things in that case. And I think too much about that. Well, we think we have research like this, but there are problems. And also, I mean, what we wanted to do was to show something like this for coaction, and then show that their result is corollary on other results that it comes from taking composition of the coaction factor and the cross product factor. But did manage that in fact the proof we have sort of uses their results to prove something about coaction, and then it's something meaningless to use that to show their theorem again. It would be a circular argument. Okay, so well, basically, if on the first attempt you think that this tensor D construction and ESation was kind of the same, but there's a map from one into the other. But the problem is that this we don't know that this map is injective because we are land on maximal tensor product. So that's another problem. Oh, and then, well, that's some, at least increase amenable at infinity, then it's going to be. And well, so, the final remark, but we saw that we needed two kind of functions, some going into the max tensor product and some going into the minimum tensor product. And sort of I suggest maybe we should also look at exotic tensor product. And usually we only look at the minimum and maximal tensor product. And probably there are a lot of C-star tensor products in this. Maybe people in the study haven't really seen it. So, I think
But all the products are subject, or you assume.
yeah, but what should study C-star, C-star norms on the right which are between the maximum and
They are multiplicative.
yeah, so it's, and of course we should simple templates. So Okay. Yeah. All the things you should study is what are really these cross products. It's an example of a row algebra, but if you look into row algebra, you quickly get into something much more general. So this algorithm was quite well.
So what are the row algebras? Can you remind me?
Well, this is an example.
Yeah, I got that. Yeah.
And it's start to do with triangles and this more. Yeah. It's more general. It's group accidents. It's a method.
Of course, yeah, it's okay.
It's geometry. Yeah, I think that's what I wanted to say.
Okay, thank you so much. Okay, so let's begin with a fury of questions. Any volunteers? Tomek, Francesco, first row.
I have only one notational remark. If you could come back, you have 2 pages on which we are using this balanced tensor product over G. In fact, if you look closely into the definition, it's a cotensor product. So this box should be used. Here, for instance, yes? On top. On the top, yeah.
Yeah. Well,
Which makes some philosophical difference between.
Yeah, because one is a sub-construction, one is a quotient construction.
Yes.
No, I fully agree with Tomek. That's, I mean, cotensor products are well established in mathematics. There's no need to avoid them. Okay. And indeed, that's what's happening. Yeah, I like it. I agree.
yeah. Yeah.
Because you restrict them, but that's agree, right? It's a restriction, it's not a quotient. Yeah, that's very important. Different factoriality.
And this plays a role when you are starting thinking about exactness of something. Sure, those. This tensor product and the cotensor product have different exactness properties, or non-exactness, different derived factors, left exact, right exact.
Okay, good. Anybody else? How about you? No question.
I have just a question. Later on, you have M tilde.
Yeah.
So is it just multiplier algebra or why is it?
Well, he defined it out of multipliers, but I also don't understand
I
it.
didn't get it.
It was too fast, yeah.
Yeah. Well,
Yes, but here's a definition, but so M have usual multipliers, but then if you have some union, have some additional conditions, so
yeah. If you have an action or group on an algebra. So for this, you think of that as a map from G to algebra, fix an element. That function is not in C, not in It's in fact it is uniformly continuous. And if definition here, if you replace C star B with E naught of X, then you exactly will get continuous functions.
The other most important question is last remark, because we were wondering about this use of maximal tensor product also with Piotr and Tomek. So he was right in which paper? It is some remark in
Yeah, well, he wrote a paper, I think, about this kind of action where we used maximum tensor product.
Okay, so maybe later I will ask you precise reference if you remember.
Yeah, of course,
I'm still confused about this M tilde. So you mean that there are some multipliers which do not satisfy, right? But M1 tensor C is not in a tensor C, but
Yeah,
how come?
well, so you want,
Because one is not in A.
That one, okay, thank you.
Otherwise, you don't need multipliers.
Exactly, thank you, Francesco. I'm,
so if you have sort of
Yeah,
A and C here, then
yeah.
maybe so that's the.
So this is non-symmetric in A and C.
So, no, I should write and then.
No, what's wrong with your thing? Yeah, no, but you have to, no, yeah, perfect. Yeah, it works, it works.
Always. Nothing always.
Happy story. No, and it.
First of all, if you're interested, the place to start reading is an article here by Plus Eschler and Lilith. Survey. Arbor Symposium in 15. That's a very good article. And then of course you should read other articles to find, and also the references there. I've been rather sloppy with referring. So,
May I help you a little bit? You
can fold it. It's telescopic. You can fold.
It would be easier to write if you fold.
oh, yeah.
Oh my.
I mean, I have sort of done very similar. So B means read bar, Nathan bar. So we should read
BBB.
So we should read that as E is secret hole. There. W is over here smart. Or so I'm at least and then of course there are others. So if you start with this, continue the references.
Anybody else? No volunteers yet. Anybody on Zoom? Mark? Do you have any questions, perhaps? No? Paul is gone. Elmar, no questions?
No, thanks.
Okay, good. Adam, last call.
Okay, so maybe let me ask one question. So the classical Baum-Kohn conjecture has far-reaching implication, and those far-reaching implications are from both possibilities that this map is surjective and also that this map, assembly map, is injective. So how about your version of Baum-Kohn?
Well,
is it also in different flavor, demanding that this map would be surjective, some topological consequences?
I don't think it was discussed. I understand your question because I wanted to ask a similar question, but I think your question somehow implicates that there was anything about Baum-Kohn in this context of coactions, right? I mean, I didn't see any, or am I wrong?
I guess you can formulate Baum-Kohn conjecture for coactions.
But okay, but it's not done, right?
No, I don't think so.
Okay.
I mean, there have been variation for quantum groups.
Surely Nest and Meyer.
Yeah.
Yes. Because you see, when it comes to this work of Paul Baum, Hübner and Willett, right? Then indeed, when using the typical reduced cross product, there were counterexamples to the conjecture. I don't remember whether it's activity or subjectivity effect. I'm sorry, this I don't remember. I don't know. No, not that I don't remember, I just don't know. But then they realized that if they replace this cross product, change it from reduced to exact, all of a sudden it works. It fixed the conjecture. So the assembly map was an isomorphism after they switched from reduced to exact cross product. Okay. So I understand, Adam, that your question would be like, okay, let's formulate this Baum-Kohn for coactions, meaning Baum-Kohn with coefficients, because saying Baum-Kohn for coactions doesn't make sense. I mean, it's a Baum-Kohn with coefficients where you construct somehow cross products using coactions instead of actions. Okay. And then, of course, I would expect that the same is true, that you might find some counterexamples for reduced coactions, and it's fixed by having exact coactions. But it's too early into the day to. Yeah.
Okay, thank you.
All right.
I have a question. So at up to some moment, you didn't need exactness. At some moment you started speaking about exactness, but I'm interested how far you can go without this exactness.
Well, what we did sort of, you can construct coactions
Yes.
similar to bending, and then you can start asking questions about when is this exact, compatible.
But my impression was at some moment that your intention was to replace exactness by some properties of some coactions.
No, not really.
Not really.
Yeah, we want to.
It's not an alternative approach.
No.
You are ending up
in
in exactness.
Yeah. And we want to.
But through coaction.
Exact coaction.
Yes.
Or really coaction factors.
But you could ask which coactions lead to this Baum-Kohn with coefficients, even if they do not lead to, if they do not demand exactness for this. Yeah. Because exactness is some formal condition which is sufficient to get this conjecture by formal manipulations, like in homological algebra. Okay, but maybe exactness is not necessary for.
Yeah, but remember this theorem of Gromov, where one hand side, when you take reduce, is not exact, and the right hand side is exact. So you really need to fix it. There is a deep problem. The left and right hand side of a Baum-Kohn have different properties if you insist on being reduced. Okay, so unless you fix this exactness issue, there's no reason to expect for Baum-Kohn to hold except by some freak of a chance. Yeah. So can you go back to this Gromov theorem, because I think this is very important. At a certain moment, you had the Gromov theorem.
No, I think we didn't really state it. I think we just said that.
No. Yes.
Yeah.
Yeah, that's the problem. Yeah. Like topological K theory, I mean, K homology is an exact functor of fractions, but reduced cross product is not. And you have to fix this.
Yeah, but
Exactness of-
but this means that the exactness is sufficient,
Yes,
but maybe it's not necessary. Maybe there are some properties of these corrections guaranteeing that this Baum with coefficient holds, even if the group is not exact, or even if this correction is not exact.
Well, the one side is exact.
exactly. I don't get your point.
Then you have to change that side
Yeah.
too.
Yeah. If you want to keep the left-hand side,
Hmm.
then the right-hand side has to be exact.
Yeah.
You can argue in what sense, in what way, and so on, but you have to have this matching. Anyway, just remember that it was a big deal in Baum-Kohn because people were used to tweaking the left-hand side of a conjecture, the topological side.
But the isomorphism maybe is not a transformation, it's just isomorphism of groups or this is not that we are comparing functors, but maybe
Yeah.
just the groups.
It's one point, and the second, my point was that this is not about this construction, which is exactly about K theory of this. So maybe.
Yeah, of course, yes, of course. It's you need at the end of the day we need like K exact.
Yeah. Oh yes.
Yes,
Yeah. So okay.
Yeah.
So maybe
Yes.
the story is about some
Yes.
kind of K exactness.
exactly,
Okay.
exactly. Yeah, now we agree.
So you don't want more exact, but less exact.
Yeah, but yeah, because it's more general, it's okay, now I've got you. Yes, we established the point. So I think it's a good time to wind it up. So let's thank Magnus again. We stop recording.